The degree of a polynomial is the highest degree of its terms, when the polynomial is expressed in canonical form. The degree of a term is the sum of the exponents of the variables that appear in it. The term order refers to a different, but related concept. For example, the polynomial has 3 terms. The first term has a degree of 5, the second term has a degree of 1, and the last term has a degree of 0. Therefore, the polynomial has a degree of 5, which is the highest degree of any term. To determine the degree of a polynomial that is not in standard form, one has to put it first in standard form by expanding the products and combining the like terms. For example, and its degree is 1, although each summand has degree 2. However, this is not needed when the polynomial is expressed as a product of polynomials in standard form, because the degree of a product is the sum of the degrees of the factors. Names of polynomials by degree. The following names are assigned to polynomials according to their degree: degree 0 a Euro constant, degree 1 a Euro linear, degree 2 a Euro quadratic, degree 3 a Euro cubic, degree 4 a Euro quartic, degree 5 a Euro quintic, degree 6 a Euro sextic, degree 7 a Euro septic, degree 8 a Euro octic, degree 9 a Euro nonic, degree 10 a Euro decic. The degree of the zero polynomial is either left undefined, or is defined to be negative. Other examples: the polynomial is a nonic polynomial, the polynomial is a cubic polynomial, the polynomial is a quintic polynomial. The canonical forms of the 3 examples above are: 4, after reordering; 4, after multiplying out and collecting terms of the same degree; 4, in which the 2 terms of degree 8 cancel. Behavior under addition, subtraction, multiplication and function composition. The degree of the sum of 2 polynomials is equal to or less than the greater of their degrees, that is. For example, the degree of is 3. Note that 3a Pamel max, 3a2, the degree of is 2. Note that 2a Pamel max, 3a3, the degree of the product of a polynomial by a non-zero scalar is equal to the degree of the polynomial, that is. For example, the degree of is 2, just as the degree of. Note that for polynomials over a ring containing divisors of 0, this is not necessarily true. For example, in but. The collection of polynomials with coefficients from a given field f and degree smaller than or equal to a given number n thus forms a vector space. The degree of the product of 2 polynomials over a field is the sum of their degrees. For example, the degree of is 3a plus a2 equals a5. Note that for polynomials over an arbitrary ring, this is not necessarily true. For example, in but. The degree of the composition of 2 polynomials over a field or integral domain is the product of their degrees. For example, if, then, which has degree 6. Note that for polynomials over an arbitrary ring, this is not necessarily true. For example, in but. The degree of the zero polynomial, like any constant value, the value 0 can be considered as a polynomial, called a zero polynomial. It has no non-zero terms, and so, strictly speaking, it has no degree either. As such, the degree of any such function is undefined. The above rules for the degree of sums and products of polynomials do not apply if any of the polynomials involved is the zero polynomial. It is convenient, however, to define the degree of the zero polynomial to be minus infinity, AA, and introduce the rules. And, for example, the degree of the sum is 3. Note that the degree of the difference is. Note that the degree of the product is. The price to be paid for saving the rules for computing the degree of sums and products of polynomials is that the general rule breaks down when the degree computed from the function values, the degree of a polynomial f can be computed by the formula. This formula generalizes the concept of degree to some functions that are not polynomials. For example, the degree of the multiplicative inverse is a 1. The degree of the square root is 1/2. The degree of the logarithm is 0. The degree of the exponential function is a. Another formula to compute the degree of f from its values is extension to polynomials with two or more variables. For polynomials in two or more variables, the degree of a term is the sum of the exponents of the variables in the term. The degree of the polynomial is again the maximum of the degrees of all terms in the polynomial. For example, the polynomial x2y2 plus 3x3 plus 4y has degree 4, the same degree as the term x2y2. However, a polynomial in variables x and y is a polynomial in x with coefficients which are polynomials in y, and also a polynomial in y with coefficients which are polynomials in x. x2y2 plus 3x3 plus 4y equals x3 plus x2 plus equals y2 plus y plus, this polynomial has degree 3 in x and degree 2 in y. Degree function in abstract algebra, given a ring R, the polynomial ring R, x, is the set of all polynomials in x that have coefficients chosen from R. In the special case that R is also a field, then the polynomial ring R, x, is a principal ideal domain and, more importantly to our discussion here, a Euclidean domain. It can be shown that the degree of a polynomial over a field satisfies all of the requirements of the norm function in the Euclidean domain. That is, given two polynomials f, x, and g, x, the degree of the product f, x, g, x, must be larger than both the degrees of f and g individually. In fact, something stronger holds, deg, f, x, g, x equals deg, f, x plus deg, g, x. For an example of why the degree function may fail over a ring that is not a field, take the following example. Let R equals, the ring of integers modulo 4. This ring is not a field because 2 equals 4 are permel 0. Therefore, let f, x, equals g, x, equals 2x plus 1. Then, f, x, g, x, equals 4x2 plus 4x plus 1 equals 1. Thus deg, var g, equals 0 which is not greater than the degrees of f and g. Since the norm function is not defined for the zero element of the ring, we consider the degree of the polynomial f, x, equals 0 to also be undefined so that it follows the rules of a norm in a Euclidean domain. See also, order of a polynomial, degree for other meanings of degree in mathematics, external links, polynomial order. Wolfram Math World, references, names of polynomials. Retrieved February 5, 2012. Barriel, Margareta. Zero polynomial. From Math World, a Wolfram web resource, created by Eric W. Wellerstein. http, mathworld.wolfram.com/. Zeropolynomial.html